Okay, I thought I'd wrap up section 4.5 by using the guidelines in on page 395 and going through a couple of different rational functions and sketching the graph. So you can look at the guidelines yourself, and they're in a particular order, but as you can see here, this is really the order that you want to follow. They're in a slightly different order there, but probably the easiest way to figure out, how to sketch a graph, I would do the asymptotes first, verticals and horizontals, or even oblique if they exist. That way you can get a framework as to where the function's going to lie. Once you know the regions where they're going to lie, which are kind of set aside by the asymptotes, then the next thing really to do would be to get the intercept points to figure out where this thing actually crosses the x and y axes. And then finally, and this is optional, there may be times where you want to get some other points. Maybe the curve is dipping down and coming back up, and you'd like to find out roughly how far down it goes. Sometimes you'll need to calculate one or two other points just to help you sketch the graph. But again, that may or may not be the case. So let's look at this rational function here, and let's get started. First thing we want to do is look for asymptotes. So we'll start with the vertical asymptotes, if there are any. And again, vertical asymptotes are the zeros of the denominator. In other words, if this is 0 down here, you can't have 0 as the denominator of a fraction. That's not allowed, so that would create vertical asymptotes. So to do that, just find zeros of the polynomial down in the denominator. So all we're trying to do here is factor this or solve for x. And in this case, this factors into x minus 3 times x plus 1. Again, we have techniques to figure this out that we learned earlier. So what are my zeros here? X equals 3 or x equals minus 1. So let's go ahead and put those in on the graph. So minus 1 is here. We'll go 2 spaces per unit. 1, 2, so there's plus 3. So we have vertical asymptotes there. So by getting this in right away, kind of helps us to figure out where the curve's going to lie. All right, let's take a look at horizontal asymptotes. Again, for that one, we compare the degree of the polynomial in the numerator with the degree of the polynomial in the denominator. In this case, we have a 2 here. So let me write this. Horizontal. Okay, so horizontal asymptote. And the degree of the poly in the denominator is also 2, so it turns out they're equal. When they're equal, that means the asymptote is the line at y equals a over b, where a is the leading coefficient of the numerator, which happens to be a 1, over the leading coefficient of the denominator, which also happens to be a 1. So that's just 1. So at y equals 1, we have a horizontal asymptote. So the graph is going to fall somewhere in these regions, and hopefully the intercept points will help us there. Okay, So, one more question before we get started. Vertical asymptotes, you can never cross them. They're not in the domain. Horizontal asymptote, on the other hand, the graph may cross it, may not cross it, we're not sure, so we have to run that test. And that test was, if that's what the function equals at the asymptote, then set the function equal to that and solve for x. If we get a solution, then that's the point on x where we cross the horizontal asymptote. So again, set the function equal to its value on the asymptote, that's the y value is 1, and solve for x. Well, if I multiply both sides by this whole quantity, 1 times this is just that value, so okay, we need to solve this. Well, these x squareds are the same, so if I subtract x squared from both sides, I would get that. If I go ahead and add 2x here, that'll take that out. And then if I add that 2x over here, that's 5x. And then finally, if I divide both sides by 5, minus 3/5 equals x. So we have a solution here. So that means on the x-axis, when x equals minus 3/5, and that would be somewhere in here, we're going to cross the horizontal asymptote. So we're going to actually, our graph will go through there at some point. So we don't know if it's coming down this way or going up this way yet. Let's look at the intercepts now. Okay, y-intercept, we'll do that one next. That's the easiest one. Again, y-intercept means when do I cross the y-axis? At what point? Well, again, if you're on the y-axis, x is 0. So just put 0 in for x. So in other words, we're evaluating the function at 0. So all these x's become zeros. So 0 on top, minus 3 on the bottom, with 0 in the numerator of a fraction means it equals 0. Okay, so the graph is actually going to cross the y-axis here at the origin. Okay, so right away we can see that if I got to go through these points, we're probably doing something like this. Okay, let's take a look at the x-intercepts. They're a little more difficult, but not that bad. Remember, on the x-axis, y is 0. So to find the x-intercepts, I want the function to be 0. But the only way this fraction can be 0 is if the numerator is 0. So we just want to solve that for 0. So in other words, to find the x-intercepts of a rational function, find the zeros of the numerator. Well, this factors. Can factor out an x. So what does it look like here? It looks like we got 0 and we got minus 3 as x-intercepts. But let's look a little deeper. First, I got to make sure neither one of these was outside the domain. So go back to the vertical asymptotes, and no problem, these are different, so we can use them both. Then the other question, do we go through those points or do we bounce? Well, again, go back to your rules. If we have an odd power there, in other words, an odd multiplicity, and these are both 1, that means they go through the point. So if I go to -3, 1, 2, 3, my curve is going to go through that point. And if I go to 0, I'm going to go through that point. So it turns out the x-axis and there's an x-intercept and y-intercept that are actually the same. So I think we got enough to do it now. If you take a look at this point, okay, we got to go through it this way or this way. Well, if we go through it this way, we're going to run into a problem. So we have to go through it like this because we're trying to get closer and closer to these intercepts but never touch. So that's the only possible spot. What about here? Well, again, this is pretty obvious. If I got to go through these 2 points and I'm doing this, and as I come out of here, I just have to continue to get closer and closer to this. So again, what we're doing here is we're doing rough sketches of rational functions. We're not getting it right to the, to the point, but we're getting an idea here. Okay, but look, all of this is also in the domain. So where do these x values go? Do I go here and try and cross, or do I go up here? Well, if the curve continues down here, I would have another x-intercept, and I don't have any more. So that means the curve out here cannot cross the x-axis, so that forces it to be up here. And there's the graph. And what I'm talking about by other points, if you wanted to be a lot more accurate here, you could say go to the point 1, evaluate the function when x is 1, and you would get a y value, and you could get a little more accurate, but that's up to you. Okay, let's look at one more problem here. Okay. In the last one, we had horizontal and vertical asymptotes. This one's going to be a little bit different. First thing we're going to do is check for a vertical asymptote or asymptotes, and we're going to discover we don't have any, but we'll see that in a minute. And then when we look at horizontal asymptote, we're not going to have the horizontal asymptote either, but that means we either have an oblique, or in other words a slanted line, or a nonlinear or a curved line for an asymptote. So let's start with the vertical. Okay, vertical asymptote. Again, what do? We look at zeros of the denominator. So that won't factor, but I can subtract 2 from both sides. But then if I take the square root of both sides, x is going to be the square root of a -2. That would introduce an I. This is a complex number. So what does that mean? By the way, that's plus and minus when I do. I have 2 complex roots. They're not real roots. So no real roots or zeros. No real roots means no vertical asymptotes. Vertical asymptotes only occur at real roots of the denominator. Okay, so we don't have anything to sketch in. Let's check horizontal. Again, for horizontal asymptote, We want to compare the degree of the top polynomial with the degree of the bottom polynomial. Okay, in this case it's greater. That means we're going to have a non-horizontal asymptote. Since it's non-horizontal, that means it's going to have an equation. It's going to be the equation of a line, or it's going to be the equation of some sort of a nonlinear curve. Okay, again, how do we get that equation? Just do the division problem. Notice that's a 2, so synthetic division is out. So we have to use long division here. And again, you want a zero fill. So I'm missing an x term here. So we're going to put in 0x plus 2. We're going to divide that into the top. We've got x4. We don't have an x cubed, so let's zero fill that one. Minus 5x squared. No x term, so let's just zero that guy. And then plus 4. Okay, so again, leading terms, x squared times what equals x fourth? It would be x squared times x squared, so let's put that here. Multiply this times this, x4. They match, that's what we want. X squared times x is x cubed, so there's 0 x cubes here. And then 2 times x squared is plus 2x squared. Draw a line, subtract. This is 0, that's what we want. These are all zeros. Minus 5 minus a plus 2, that's minus 7x squared. Okay, bring down the next term. So there's nothing there, so let's go ahead and bring down the next term, which would be a 4. Okay. X squared times minus 7 would equal this, so we want a minus 7 here. Minus 7x squared. Minus 7 times 0, that's 0 x's. And then minus 7 times a plus 2, that's minus 14. If you subtract these, that's minus 7 minus a minus 7, that's a plus, so they cancel, and that's what we want. These are zeros. 4 minus a minus 14 would be 4 plus 14, that's 18. That's the equation of a nonlinear asymptote. We're going to have to graph this, guys. That's a whole nother problem. Okay, again, why nonlinear? Because the degree here is not 1. That's all. Before we graph it, since this is pretty easy to do here, are we going to cross this nonlinear asymptote? Well, the answer is no, because you cross the asymptote for the zeros of the remainder. But what are the zeros of the remainder? If I set 18 equal to 0, that's impossible. So there are no zeros, so this graph will never cross the nonlinear asymptote. So we don't have to worry about that. So far we've had nothing to put on our graph. Now we're going to have to put this on the graph. All right, so let's look at this. What we're going to be graphing here, let me get down here, do it here. y equals x squared minus 7. We're out of this problem right now, and we're just trying to graph this as an asymptote. So what would that look like? Well, if you recall back at chapter 3 with the toolbox kit and the transformations, if you look at this as just y equals x squared, that would look like something like this. That's a parabola starting at 0, 0, and it goes through minus 1, 1, and 1, 1. But now we're going to shift it down 7 units. So this is going to come down to minus 7, but we're still going to be on the y-axis, so it's going to be 0 for x, but we're going to come down 7 on the y-axis. So this point's going to move down here. And then these points here, you can recalculate with the table if you want and get extra points, but I think we can figure it out. If this is the point, x equals 1, y equals 1, well, this doesn't change x. So x is still going to be 1. Over here, x is still going to be minus 1. But instead of being at y equals 1, we're going down 7. So I'm going to go down to minus 6 on each of these. Okay. Or you can set up a table, pick some x values, calculate some y values, and come up with some points that you could plot to help you get this curve in there. Also, this family here opens up, and we know that because we had a positive x squared. So this is all stuff we learned from back in like chapter 3. All right, so let's go down to minus 7. That would be here. So that's where the parabola starts, and it's going to open up, and it's going to go through the point 1. And I'm using ones here, 1, 2, 3, 4. On the x-axis, since I know it's going to be coming up, what I want to go ahead and do is use 2 units for 1. So in other words, 1, 2, 3, like that. It's going to make the graph look better. Minus 1, minus 2, minus 3. So what we want to do is go to x equals 1, which would be here, and we want to go down 6. That would be here. Over here, same thing. And remember, with the parabola, they're going to mirror each other. So I can start to get an idea of how this is going to go. I think what I'm going to do, just to kind of get a really nice graph, is I'm going to figure out what the x-intercepts are for this curve right here. So that would mean, what is x when y equals 0? Well, if I add 7 to both sides, and then I take the square root of both sides, and then I get my calculator out and I look at the square root of 7. Square root of 7 is roughly 2.6. So I would have plus 2.6 or minus 2.6 on the x-axis. So 1, 2, 2.5, so about there. And over here, 2, 4. So this is the idea of calculating extra points just to help you get a little bit better drawing. So let's sketch it. And again, we always used a dashed line because that indicates an asymptote. So we're looking something like that. Okay, next we need y-intercepts and x-intercepts. So y-intercept, again, that just means where do we cross y when x is 0. So we're evaluating for y-intercept, we're evaluating the function as 0. So 0 to the 4th minus 5 times 0 plus 4 over 0 squared plus 2. That's going to equal 4 over 2, which equals 2. So at y equals 2, our curve crosses. What about x-intercepts? Again, if you remember, for x-intercepts, that means when does the function equal 0? The only way the function can equal 0 is when the numerator of the fraction equals 0. So again, for x-intercepts, we want to know when does the numerator equal 0, or zeros of the numerator. Okay, now we got to go back and use some techniques that we've learned before. And that is, when I look at this, what this really looks like is x squared minus 5x plus 4 equals 0, which I could easily factor. But that's not x squared and that's not x. But if you look at the smaller power, if you square it and it becomes a bigger power, that's a good candidate for u substitution. So what we want to do here is let u equal x squared. And we're going to substitute u in here. So look what happens. If u equals x squared, u squared would equal x4. Here we just replace x squared with u. Okay, now we just factor this thing. U minus 4 times u minus 1. Okay, again, let's notice a couple things before we move on. Each of these has a 1, so we know our graph is going to go through these x-intercept points. It's not going to bounce. If these were even, it would bounce. Okay, so we're going through. So right now I have u equals 4 or u equals 1. But I need x. So back to your substitution and put each of these u values into here and solve for x. So when u equals 4, or when u equals 1, well, the way we solve these is we take the square root. So square root of 4 is 2, and that's plus or minus root. And over here, square root of 1 is 1. So there's my 4 roots. And again, let's just do a sanity check. These are 1s. That means there's no multiplicity. The degree of our polynomial was 4, so we're expecting 4 roots, and that's what we've got. Okay, so these roots are x-intercepts. So we're at plus or minus 1. We're here. Plus or minus 2, we're here. Okay, so since my curve has to get from here to here, it could go this way, but the problem there is I'm not going to be able to go through this point. So I've got to go like this. And then I'm not going to do it, but if you were interested in how far this goes, we know it can't go this far. It can't cross, but you could maybe put in 1.5 and see how far down it goes. I'm not going to do that, but that would give you a little more accuracy. But I just know roughly it's going to come down like this, and it's going to come back up through this point, and it's just going to get closer and closer to our asymptote. And that's it.